Hello, thank you very much. I'd like to start by thanking the organizers for setting up this great event. Thank you very much for that. I'll talk today about some problems and results on counting Hamiltonian cycles, and the main focus will lie on graphs with few Hamiltonian cycles, because of this phenomenon that in many interesting graph classes, whenever you have one Hamiltonian cycle, you seem to have many, but which is not very well understood. And I also focus mainly on regular graphs. So that's a setting. Much of this work is motivated by a conjecture certainly famous in the field by John Sheehan, which states the following. So you have a 4 regular graph. So that's a graph in which every vertex has degree 4. And the conjecture states that if you assume the presence of one Hamiltonian cycle, then you will have at least 2. And this turned out to be quite tricky problem. And so people have looked at some variants, and this is still open. And one natural thing you can ask is, well, let's replace this 4 by some natural number k, right? What can we say then? And just like to point out a few contributions on this. So Andrew Thomason showed a more general result, but which implies that for every odd integer, this is so. Right, so every Hamiltonian k regular graph has at least 2 distinct Hamiltonian cycles. If your k is odd, then this works, and he devised a nice method for this. It's called the lollipop method. And Carsten Thomason, so two very much different people here. He made also some important contributions to this. So he used Andrew Thomason's result, well, just in the sense that for odd k it's done, and then observed that if you assume Sheehan's conjecture to be true, and also use Peterson's two-factor theorem, a classic theorem, then you have it for all k, except for cycles. It's not interesting, but for k at least 3, right? So Sheehan's is just to point out, this is not difficult to see, but it's fundamental, because this is just to point out that this 4 here is fundamental. If you can do it for 6 or 8 or so, you won't get this total result, right? You won't get it for all the k. But if you can do it for 4, you can do it for everything, taking these remarks into account. Okay. But Carsten Thomason also made a much more substantial contribution here. So in the first paper, he gave a certain structural description of these problems, and then in a follow-up paper, he used Lovaas's local lemma. So the first part is deterministic, then Lovaas is probabilistic, to show that this is true if your k is large enough. And then he showed it, I think in his paper, he shows it for k at least 300. Then there is a note added, which tells you that if you are more careful with the parameters, you can do it for 72. And then other people have further refined this. And right now we are at 22 by Haxel, Simon, and Verstraete. So that's at least 22. And they say also, well, with even more work, probably you could push this down slightly. You can get a slightly smaller k. But as Thomason himself writes, and it's not a very long argument, but I don't want to repeat it here, you cannot go all the way down to 4. So even if your proof here, you do 300 pages, it doesn't matter. There is a structural impediment to that, to pushing it with this method, with his combination of this semi-deterministic, semi-probabilistic proof, which is, by the way, really short, but I would say quite ingenious. You cannot push it all the way down to 4. So something else will be needed. Then there's this result of Girao, Kitty-Passon, and Narayanan, which deals with a much larger class of graphs, but is related. So if you take a graph on n vertices, minimum degree at least 3. So of course that includes 4 regular graphs, but a much larger class. And it has one Hamiltonian cycle. So you can draw these graphs just by putting your Hamiltonian cycle down and then just adding chords, right? And from every vertex, at least one chord must emanate, because the minimum degree is at least 3. Then This graph will contain another cycle of length at least, and you see the quantity here, n minus constant times n to the 0.8, to the 405. And they also have a very nice conjecture, I think, really important conjecture in this direction, which I'll mention at the end. But this is the result, so we do know this. A slightly different direction, so back in 1980, Entering and Swart, they showed that there are infinitely many graphs containing exactly one Hamiltonian cycle. These are called usually uniquely Hamiltonian, in which all your vertices are cubic, so they have degree 3. If I'd stop the sentence there, that would be impossible, right? Because we saw that for 3 regular, it's not possible. But 2 exceptions. So you allow 2 exceptions. 2 vertices are 4 valent, so have degree 4. Then you can have exactly one Hamiltonian cycle. And then they asked whether here in Sheehan's conjecture, I'll go one slide back. Here in Sheehan's conjecture, actually, the 4 regularity is important. Can't replace that just by a minimum degree 4 or minimum degree at least 4. But answer is negative. So Herbert Fleischner showed that there are infinitely many graphs containing exactly one Hamiltonian cycle, in which every vertex is degree 4 or 14. In fact, you can say much more. So Brinkmann and De Paul recently showed that for very many degree sets, you can do this. So your degree set is here, this M. This is what you should look at. So you start with a 4, and then you have some increasing, some integers here bigger than 4, and you can have uniquely Hamiltonian graphs with exactly this set of degrees occurring, with 3 exceptions, and that's 4. That's just Sheehan's conjecture, right? 4 and 5, and 4 and 6. So about those, we don't know whether you can build uniquely Hamiltonian ones. Okay. I want to talk about 2 conjectures of Haythorpe, which are very much related to this. So the first one that you see here is exactly about the class in which also Sheehan was interested, so the Hamiltonian 4 regular graphs. And Haythorpe conjectured that this here should be a lower bound on the number of Hamiltonian cycles in these graphs. Okay. And the second conjecture is you don't need to read it all. It's just about K regular graphs for K greater than 4, right? So he conjectures this for the lower bound here, for the number of Hamiltonian cycles. Okay, so let's look at the first one, the first conjecture. So this is here the conjectured lower bound. It turns out it's not true. And it's not true in a strong sense. So Carsten Thomas and I, we showed that in fact, you can find a constant, positive constant, such that there are infinitely many 4 regular, 4 connected graphs, each with this constant number of Hamiltonian cycles. Proof is not so difficult, but we were surprised. But you can do it for a constant number, and then these are far from planar, and I was wondering what happens for planar graphs. So I did have to lower the 4 connected to 3 connected here. You can't go higher, of course, than 4 connected in 4 regular graphs, but I did lower it from 4 to 3. But I added this condition of planarity, and then I could show the same result. You also have such a constant. And now you might wonder, well, let's combine these 2. Let's do 4 connected and planar, right? What happens then? Then you cannot do such a theorem, because there is a theorem of Brinkmann and van Klempert, which tells you that there is at least a linear number of Hamiltonian cycles in this class of graphs. And this is also an open question here. So we do have a family which has a quadratic number, but where exactly? So and it seems that quadratic should be here the right number, but we can't show that at this point. It's just linear what we can prove, but certainly cannot find such a constant as in the first 2 theorems. Okay, so I repeat here his first conjecture, and now I've told the story not in a chronological order. So this appeared, and then with Jan Hutrebeur and Barbara Meersmann, we attacked this computationally first. This is back in 2020. And what you see here is just a table. First row is the orders of a graph. Second row is the number of Hamiltonian cycles. So what we do here is I'm showing you the minimum number of Hamiltonian cycles in a Hamiltonian 4 regular graph on that order. And it's important to emphasize it's Hamiltonian, right? Your graph, because otherwise many of these minima would just be 0. But and this is exhaustive, so we checked them all, and these are the minima that you reach, and these minima here, they are exactly what Haythorpe conjectured, right, up to order 21, and so we did for a while try to prove it, or prove something in that direction at least. So we were very much misled by this computational results, by these computational results. But it turns out that this 144 is kind of special. So I showed that from 19 onwards, so if your order is large enough, then you have 4 regular graphs with exactly 144 Hamiltonian cycles, right? Of course with 0, but that's not interesting. But if you have 1, you have these minima are the true minima are at most 144. And I in fact I believe 144 to be optimal for sufficiently large orders. So this is the second conjecture of Haythorpe. This is again this lower bound he conjectures, and I showed that it's not true for 5, 6, and 7 regular graphs, and then we refined this. It's a construction basically. We refined this in a paper with Jan Guttruber, Jorik Joken, Solomon Loh, and Ben Simon, and we showed that it's not true for any k. So it's not the right bound here that we are certain of, and but this was yeah, there was a variation of this proof, and I will talk about that in a moment. But in this paper here, we also answered some questions of Thomassen and of Haxel, Simon, and Verstraete. So in this paper, we made some progress, at least some partial progress on these problems. So if you fix your k, that's the degree of all of the vertices, right, in the regular graph, in a k-regular graph, and Cn then as a free parameter, then these upper bounds we have seen are all asymptotically the same quantity. And in fact, Jorik Joken, and you see here, down here is what he could prove. He showed that you can provide exponential improvements to this asymptotic upper bound, right? So this conjecture 2, for k regular graphs with k at least 5, does not only involve an incorrect constant factor, but is also asymptotically not accurate. So this is Joken's result down here. Perhaps the exact quantity is not that important, but it's less than what was previously known. There's still a huge gap, of course, between this bound and the minima that perhaps we can deal with in certain graphs that we are simply not able to describe. We don't know. So this is unclear. Let me close with some open problems. So with Carsten Thomassen, as I mentioned, we could show here this result that you see here. Just make out of it a statement, replace a 5 by a 4, and then we have this. But what about the 5 regular 5 connected case? We have no idea. You definitely need a new idea to get this result, and if it's true, and if it's not, that would be also very interesting. So we would like to know this. And then I already mentioned that there is a conjecture, very nice conjecture in this paper of Girao, Kittipassar, and Narayanan, and it states the following. So if you have an n-vertex graph, again with minimum degree at least 3, that's what this means here, and you have 1 Hamiltonian cycle, then in fact you can find another cycle which will have length at least n minus some constant k. Your k will need to be greater than 0 because we know that this class here contains uniquely Hamiltonian graphs. So if you just put k equals 0, then this is clearly false. But they conjecture that you can find such a constant. And in fact, Thomassen, who also worked on this a lot, he conjectures that you can do it for k equals 1. So the next best thing, you cannot find another Hamiltonian cycle, but you can find an n-1 cycle. Always. So either an n-1 cycle or an n cycle. Of course, typically your generic behavior will be that you will have another Hamiltonian cycle, in fact many more, but there are particular graphs in which are uniquely Hamiltonian, but in which you can find another n-1 cycle. And then finally, I want to draw attention to also in the context of these problems to an old conjecture of Cantoni. I think this is from the 50s. I think it was discussed by William Tutt, and he was also interested in this. That if you have a planar 3 regular graph, and it contains exactly 3 Hamiltonian cycles, these are also some interesting coloring problems, then this must contain a triangle. Such a graph must contain a triangle. And you can construct them easily. So you can start with a tetrahedron. It has exactly 3 Hamiltonian cycles. And then just cut off vertices, right? You're introducing lots of triangles, but this will stay at 3 Hamiltonian cycles, and you get an infinite family immediately. And they're planar and 3 regular. So it's very easy to describe. But why should they always contain a triangle? It's unclear, but I very much like this conjecture, so I just wanted to mention it again. Okay, thank you very much. That was my talk.